Right, in front of us is the finite difference method topic, and we are looking at actually the question that says set up the system of equations to solve the boundary value problem x double primed x double primed equals tx, x of 1 equals x primed of 1, and you have that x of 3 equals 0 by the method of finite differences with the change in t equals 1, and we have that we do not need to solve the equations. So yeah, it's popular that you don't need to solve the equations. This is an exam question, and obviously normally solving them would require the use of computer programs and other things. And hence the advice that please just do not bother to solve the problem. So now we look at the solution. Right, the solution proceeds as follows. So we're in a position to do the following. Right, what are we actually doing here? We let. Right, so because now we are speaking about the change in t, so we need to let ti. Let t sub I denote. Right, let it denote the grid points. Let it denote the grid points. And the grid points, we call them H, which is T of I plus 1 Ti, and let. Right, we let now Xi denote. Denote the approximate. Right, the approximate value. Value of X of Ti. X of Ti. What are we actually gonna do? So we will use the following. Right, the following approximations. Right, the following approximations. What are the approximations? So we need to recall what we have here. Right, the partial squared y, the partial, okay, partial squared x, the partial t squared is equal to which is the same as xi plus 1 minus 2xi plus xi minus 1 divided by h squared, like so. Moreover, okay, so this is evaluated. It is evaluated at t equals ti. Dx dt evaluated at t equals ti is approximately the same as xi plus 1 minus xi minus 1 divided by twice I. By twice h, excuse. Okay. And of course, right, and of course, if we happen to evaluate t, right, yes, if we evaluate t at t equals t sub I, the result is t sub I. Okay, so yeah, we note these. Okay, thus the differential equation can be approximated at a grid point right at a grid point t sub I by the difference equation. By the difference equation, what is the difference equation? So we've seen, therefore, the difference equation here is x sub I plus 1 minus twice x sub I plus x sub I minus 1 divided by h squared. See? Okay, because obviously we're looking at the different at this one here that says x double primed equals tx. So we can consider, just let me write something here. Can write here x double primed can write x double primed of t equals tx, which means x I plus 1 minus twice xi plus xi minus 1 for this x double primed and this is divided by h squared. Okay, and this is actually equal to, now you have the t, so the t becomes t sub I, and then the x now becomes x sub I. Okay, like so. And then now we will get the difference equation here. Yeah, we are well on track. So now let's consider this one and perform some manipulation when when the change in t is 1. Right, so when h which is the change in t, which equals 1 for this question, we obtain, right, so we're just going to put 1 here. And if we put 1 here, then it's going to just be the axis at the top, which is this minus twice xi plus xi minus 1, which is ti xi. Now the grade. Right, so we comment on the grid. So the grid in this problem consists of the following points. What are the points? So obviously we'd have to look at the initial points because this is a boundary value problem. So in this boundary value problem, you have to look at the interval to say you have x1, which is x primed of 1, and then we have x3. Right, and obviously if you look at this question, having x of 1 and having x of 3. So the understanding is therefore that we are playing between 1 and 3 here. And then now, if we're operating between 1 and 3 for the t values, it gives us the values of t. So in other words, there's a 0 here, a 0. So the t0 is 1. So, right, so the points would be t0 is 1. And then we add h is 1. So which means that we shall get a t1, which is, we add 1 to this, which is 2. t3, we add another 1, we get a 3. Then we get star. We call that equation star. Now we continue to then say that equation star needs to be applied at all grid points at which the value of the function writes the value of the function x is unknown. Okay, this usually includes all grid points in the interior of the region but whether the values of x at the boundaries right at the boundaries of the region are known or not depends on the boundary conditions what are the boundary conditions the boundary conditions in this case right we have stated the okay so okay we'll continue please so you have the boundary conditions and we stated them here and I'm going to restate them again here as well so that we are just on the same page. I know that we have written the boundary conditions first, but now we're going to write them again. So yeah, the boundary conditions here are x of 1 equals x primed of 1. And then x of 3 equals 0. Right. So we have these boundary conditions in this problem here. In this case, x0 is equal to right. So in this case, you have that x0 is equal to x0 primed and because this is our 0, t0 is 1. And now also we have the next one, but we need to look at this one here, how many t's there are. So it's t0, t1, I mean t2 here. See? I mean t2 here. Because T0 is 1, T2, then we stop at 3 because this is up to argument 3. We are just playing between, or variables are just between the 1 and the 3. But now that would mean that obviously we've seen that that is up to x2. X0 is this, x1 is 2, and x2 is 3. So which means that we shall have x2, which equals 0. Are both known. And therefore, we only need to apply star at the interior grid points. At the interior grid points. At the interior grid points, which are what? Right. So obviously, if these are sort of the boundaries at 1 and 3, the interior grid point is T1 equals 2. At the interior grid, so it will be the interior grid point because it's just 1. Right. So at the interior grid point, right, T1. We get the 3 equations. Anyway, let me just say we get the following equations. I need to still determine how many they're going to be. We get the following equations. We still need to work them out. Because now this is the right, the difference equation, this one. Xi plus 1 minus 2xi xi plus 1 minus 2xi plus xi minus 1, which is tixi. Okay. Now let's look at this and look at this very carefully. Hello? Okay, yeah, just 1 minute. We're continuing with this. Yes, my dear. Okay, thank you, my dear. Thank you, my dear. Okay, we're continuing, please. My apologies. Still here. I was just speaking to someone. I was just speaking to someone. Okay, right. So we're back. Okay, now let's continue and see what we get here. Because now we have seen already, we are at the interior grid points. Now, for example, when I is 0, you can write that and say it I equals 0. So this is going to be x1 minus 2x naught plus the x at -1, which equals t0 x0. So we have a t0, which is 1, a t0 there. So at I equals 1, for example, so we continue. At I equals 1, then this is x2 minus 2x1 plus x naught is t1 x1. Okay, we have t0, t1, but we have, because t0 is 1, then t1 is 2, and then t2 is 3. So we continue now, and we say at I equals 2, we have x3, 2x2 plus x1. This is t2, x2, like so. Okay, so we have this. But obviously we know the t's. We can just plug them in. However, t0 is 1. T1 is, now you just add 1 to this, you get 2, because h is 1 in this question. And then now you also have t2, which equals 3. Okay. Now we continue. Okay, but what else do we know? However, this, but there's more that we know from the boundary conditions, in particular, because we have also the boundary conditions there. So we're going to use them. We need to just explore them a little bit and look at their significance. In particular, if you look at this one, the x1, x of 1 equals x primed of 1, and the x of 3 equals 0. We analyze them and we use them. So let's just explore those, because we're going to use them to simplify these equations here. Um, okay. Okay, continue, please. We continue. Now, I was then saying that x1 of this is, yeah, x1 using the boundary conditions. Which is x3, which equals 0. Right, let's explore these. How do we explore these? We've already seen that this one here, the prime, we have said dx dt, evaluated at t equals ti, is approximately. Right, this one is approximately xi plus 1 minus xi minus 1 divided by 2h. So yeah, we are exploring this, but we're going to use it now for the prime. So let's just have that. We have that finalized. Okay, yeah, I'm analyzing these in now. Yeah, take it easy. We are analyzing exactly what is happening here. And so this one is obviously at the x0 point, because this is x0, sort of the t, it corresponds with t0. And then we're gonna use this one. But it corresponds with I equals 0. And now, thus, what do we get? What we're able to get out of these now is that this one is x0 is equal to this one here is the prime, which is this, but it is at 0, at I equals 0, so it's going to be x1 minus x subscript minus 1 over 2h. So it's exactly this that has been now transformed here. But this one now is x at a corresponding, so it's x at what? So t0, t1, you add a 1, you get 2. And then t2, you get a 3. So now this is 2 here. Like this. T0 is 1, and then you add a 1, you get a 2, you add a 1, you get a 3. Which is corresponding to this. Okay. All right, so here you still have x3 equals 0, but you can say, let me write it like so. x3 equals 0, but you can write it as x3 is x of t2. is x of t2. Right, and this x of t2 is what is equal to 0. Like so. Okay. So we continue. Now let's analyze this one. X0. Right, x0 is equal to x1 minus these other 2h, which implies that x0 is x1 minus xi minus 1. Okay. Like so. And this is divided by 2 into 1. Yeah. Okay, so which means that we have 2x0 is x1 minus this. Okay. We're exploring the boundary conditions. We need to use them to simplify the equations. And so this one, the power of this particular boundary condition is that it is basically able to give us the x1, x of subscript this, which is the same as x1 minus 2 x0. So it means therefore this one is powerful because it's going to replace the x subscript minus 1 in the wherever it features in our equations. Like here. Okay, because there's this one with a negative subscript, so we can be able to use this one. Okay, and then there's more that we need to say. And I'm going to mention that, so there's x0 and then there's y. Okay, I will mention, I'll write a couple of things there. Need to make sure that we reason, but we reason very, very carefully. So if you reason very, very carefully, now you'd have x0, x1 up to x4. So this will be x0, and then there's going to be, okay, that's fine, never mind. I'm just reasoning. All right. So having this now, we need to attribute this one. But let's say ready this x3 now, depending on how we have categorized everything. So we can see therefore that there's an x0 that goes with t0. So in other words, this one goes with x0, this one goes with x1, this one goes with x2. So this would mean therefore that x2, because it's x at t2, we call it x2, and x2 is 0. So it gives us a boundary condition. And we have therefore that x2 itself is 0. Now, so yeah, we're good. So we just have to transform this and then we're done. Okay. Right. So which means now we just take all this and we transform them to something that we can use. Now, x1 minus 2x naught plus x subscript minus 1 t0 x0 minus 2x1 plus x naught equals t1 x1. x3 minus 2x2 plus x1 equals t2 x2. With the rest of the other things, right, so I'm going to write them in yellow. Like this one here, x subscript minus 1 is x1 x subscript minus 1 is x1 minus 2x naught. Okay, what else? We also have x2 is 0. Okay, so we are able to do replacements, but there are other things like the t's as well, which are the values of the independent variables. So we have t0, you have t1, you have t2. Okay, the t0 is the one, and then you add h, and then you add another h. So which means, therefore, you have x1. Write x1 here. Minus 2x naught. Okay, there are certain things we know, like we know x naught. What is x naught? Okay, we can write it in terms of that, but it's not numerical. We don't know a numerical value for it, but we know x subscript minus 1, which is exactly x1 minus 2x naught. So here, obviously, it really depends on how you can simplify the whole thing. But so yeah, it's dependent on the root, but they're always equivalent simplifications. T0 is 1 x naught. But in some other instances, like you can find that the x naught is 2. We could put 2 here. But here, just that they made the x naught to be equal to x1 primed. So now let's look at this. What is x2? Okay, now we know x2 is 0. So we're going to put a 0 here minus 2x1. We don't know this one. And then we have x naught. T1 is 2x1. x3, we don't know. x2 is 0. x1, we leave it because it's x. Yeah, we don't know it, this one. T2 is actually 3. x2 is 0. So, okay, let's see what we can achieve here. Any simplifications that we can get, like there is a minus 2. Okay, x1 plus x1 is 2x1. Right, we are seeing evidently 2x1, which comes from adding these ones here, but these ones here will give us minus 4x naught. We move it across, it becomes 5x naught. So what about this one now? Which means that you have x naught equals 4x1. You can write like that. X naught equals 4x1. If you move the x1 to the other side. And then here, this one is going to become 0, 0. And then it's going to mean that x3 plus x1 is 0. X3 plus x1 is 0. Okay. Right, now getting this here, what else can we infer? Okay. We don't need to solve this. But this is what we have. Some of these we don't know, so like x1, we not know the explicit, so we leave everything in this form. You can always express this in matrix equation as an eigenvalue problem and solve this here. So, but it is very popular to express it in the form 2x1 minus 5x naught equals 0. X naught minus 4x1 equals 0. X3 plus x1 equals 0. Okay, like this. Like so. Okay. Right, so we've got this now, and it is exactly what we have. And we can obviously look at how further we can simplify these, but this is what we've got exactly. All right. Let me see how far, if there's anything that can be done in this question before I move to the next one. Right, you need to set up a system of equations to solve the boundary value problem by the method of finite differences with delta t is 1, and you have exactly that. So it's all right. It's okay. So we have precisely that. Okay. Next question. This is November 2023, please. Right, here is another question that appeared in the November paper. And it says this. At this point, you need to look at this very carefully and analyze these with much caution. And here is the question. Compare. Right, this is the question. A past exam from November 2023. APM 3711. Compare. Right, compare briefly the shooting. The shooting method And the method of finite differences in solving boundary value problems. By stating the main advantages and the main disadvantages of each method. Right, here comes the question, and the question is very clear, and it says you need to draw a comparison. So you need to compare briefly the shooting method and the method of finite differences in solving boundary value problems by stating the main and rather the main advantages and the main disadvantages of each method. And obviously we analyze this very, very carefully, and we give the result or the answer to this question. It came in November. Right, so here comes the solution. Is very popular, nothing strange. Right, so to actually answer this question about the actual distinctions between the two methods, we tabulate the shooting method. Shooting method and the finite. Differences. The finite differences method. Right, so we have the following. Right, so we will tabulate these very carefully. The actual advantages. The advantages would be with a plus, showing that with a plus, we are certain here to give a solution even in the non-linear case. So with the shooting method, we are sure but very sure to obtain that this shooting method will certainly give a solution even in the nonlinear case. And I'm going to actually elaborate on the actual distinction between the linear and nonlinear case. So there are linear differential equations, the non-linear differential equations, but our mostly our focus on the shooting method is on second order differential equations of degree second order. The second derivative is the highest derivative in the differential equations. So those are the most popular. Even you can see that we studied relations about the second order, but in general, differential equations have much higher order than just second order. The method of finite differences here is the advantage is that it is actually sort of less computational. It is less computational, or it requires less computational effort. And less computational effort, especially for higher order. Higher order systems. For higher order systems, there are drawbacks to this. To the shooting method, we have, the negatives now. And so negatives for the shooting method, or the sort of disadvantages with the finite differences method. More computational effort. Okay, so the shooting method now, because we need to be reducing the order, and then it's more computational effort because we misfire. Normally we misfire twice, and then in the shooting process, we get the average using the interpolation formula. So because of that, we can really say this shooting method, it requires a bit more computational effort relatively. But the method of finite differences has a disadvantage that it may not converge. May not converge. In particular, if the equation is nonlinear and the initial estimate is not good. So these are the sort of the disadvantages of both the shooting and the method of finite differences. Okay, this was in November that they asked this question, but now let's proceed and solve more problems that appeared in this paper. Right, the next question is this one. It is a question that came as well in November 2023. You let 1 2 1 0 2 5 1 0 minus 1. So with this question, you need to use the power method. Right, use the power method to estimate the eigenvalue of least magnitude. And the corresponding eigenvector. Start with a vector one 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 transpose and do 2 iterations. Okay, this one was there and it was with 12 marks. Right. Now let's look at these and look at these very, very carefully and make sure that we solve this, or to solve this one, we look at the solution to this. Solutions. Right, so we know that this power method, the word power suggests more authority and it suggests dominance. So we focus on the most dominant eigenvalue. Now they're speaking about the least one here. And you know that once they mention the least, it has to do with the inverse. So we need to obviously focus on the inverse. So now this matrix is here, and so we shall solve this question just now. We shall solve this question just now. Right, so we have the matrix A. It is exactly this one, the 1, 2, 1, and so on. 0 to 5, 1, 0, minus 1. Okay. So that we formulate the augmented matrix one to 1, 0 to 5, 1, 0, minus 1. Okay, so with this now, we continue. This one is already having a leading one with the inverse, so we need one to just write 1 to 1. 1, 0, 0. And then this one is 0 to 5. Just write it as 0 to 5 for now. 0, 1, 0. Row 3 minus row 1, 0. So multiply this by minus 1, you add. Multiply this by minus 1, you get minus 2. Multiply this by minus 1, you get minus 2. Multiply this by minus 1, you get that. You get that. You get that. Now we have the following. Right, so we need now to get zeros above and below these, but we need a 1, which is 0, 1, 5 over 2, 0, 1/2, 0. Row 1 minus row 2. 1, 2 minus 2 is 0. 1 minus 5 is minus 4. 1 minus 1, 0. And then here is row 3 plus row 2. 0, 0, 3. Minus 1, 1, 1. So now you get here 1/3. 1/3 of row 3. One-third of row 3, so it's 0, 0, 1 minus 1/3, 1/3, 1/3. Yeah, like I said, the dominant one is easier. The least is the most involving, but also the intermediate is involving. We saw that last time. Okay, right. So because this one has 3 eigenvalues anyway, because it's a 3 by 3 matrix, they can be equal to each other and so on. Okay, or they can all be different. Okay, now we have these. So let's write here 0, 1, 5 out of 2, 0, 1/2, 0. 1, 0, minus 4, 1 minus 1, 0. Okay, then we need zeros above there. So writing that matrix, you have 1, 0, minus 4, 0, 1, 5 over 2, 0, 0, 1,
1 minus 1, 0. 0, 1/2, 0. Okay. Minus 1/3 and 1/3, 1/3. Right. So we have this. So now all right. Can write at the bottom of this, okay? So row 2 minus 5 over 2 row 3. Row 1 plus 4 row 3. 1, 0, 0. Multiply this by 4, we add. Multiply this by 4, we add. So this is going to be minus 4 over 3 plus 1. Minus 4 over 3 plus 3. So minus 4 plus 3 is a minus 1 out of 3. Right, so multiply this one by 4. We have 4 over 3 minus 3 over 3. So 4 minus 3, 1 out of 3. This one is 4/3. Because multiply this one by 4, we add to 0. Right, so 0, 1. Multiply this one by minus 5 over 2, you add 0. Multiply this one by minus 5 over 2, then it becomes 5 out of 6. So you multiply this one by minus 5 over 2, you add, check. It becomes minus 5 out of 6 if you multiply this one by minus 5 over 2, and then you add to the second row, 1/2. Minus 5 over 6, multiply this one by 3 out of 3, which is 3 out of 6. Minus 2 out of 6, minus 1/3. Multiply this one by minus 5 over 2, minus 5 out of 6. Minus 1 over 3, 1 over 3, 1 over 3. Okay. Okay. Right, hence A inverse is minus 1/3, 1/3, 4/3. Minus 1/3, 1/3, 4/3. Which is 5 out of 6. Minus 1/3. Minus 5 out of 6. Minus 1/3. Minus 1/3, 1/3, 1/3. All right, now what do we do with this? Right, we take this matrix, we use it to solve this problem. But it's very important that we are certain, therefore, that this is indeed the correct inverse. Should not waste a lot of time. Obviously, to check if the matrix is the this one is the correct inverse, you need to multiply this one with the matrix original, but it's a bit of work. Okay, so looking at this one here, we're able to determine that it is the correct inverse of the matrix we started with.
So right. Just a split second. I'm just gonna, yeah, I'm just trying to look at this and make sure that I have the correct inverse, because otherwise then everything is just gonna be a mess before we proceed and do the rest of the things. With this matrix here, with this inverse. So I'm trying to look and ascertain that it's the correct one. We can multiply with the matrix A on the, yeah, and verify that it is indeed the correct one, but yeah, it is gonna be a little bit minus 1/3, 1/3, 4/3, 5 out of 6, minus 1/3, minus 5 out of 6, minus 1/3, 1/3, 1/3. So it is the correct inverse, really, without wasting much time there. So I'm excited. Right, so I've just checked that this is the correct matrix inverse, so there's no mistake there. Thus, what we do is we take, therefore, the inverse matrix, this one here. So we take the matrix, which is minus 1/3, 1/3, 4/3, 5 out of 6, minus 5 out of 6, minus 1/3. And then you have this. Okay, so we multiply these together with the matrix, the vector we were advised to start with. We multiply it with the 1, 1 vector. Right, 1, 1, 1. Because we're advised to start with this vector, and so what we get here? Here you'd get minus 1/3. This row by this column, this by this is minus 1/3. This by this is 1/3, which is 0. And then we're only left with 4/3. Right, this with this is 5 out of 6. And this with this is minus 5 out of 6, giving a 0. And we have only minus 1/3 left. This with that minus 1/3 plus 1/3, 0, leaving us with only 1/3, like so. Right, looking at this carefully, what we do is we pull the dominant one, the biggest of the entries here. Which one is the biggest of the entries? Is 4/3. So we pull it out, we pull the most giant. So we pull out 4/3. Right, factoring out 4/3 is going to leave us with a 1. Right, and then here it's going to leave us with what? Minus 1/4. And then here it's going to leave us with 1/4. Like so. And then next step, we continue, we do the same, but we take this vector and we multiply with the inverse, matrix inverse again of A. So we have here minus 1/3, 1/3, 4/3. Minus 1/3, 1/3, 4/3. Minus 5 out of 6. Right, so we have this, and then we have 5 out of 6 here.
We have minus 1/3. We have minus 5 out of 6. We have minus 1/3. 1/3. 1/3. And then now we're going to multiply this with the vector that came out of it, the sort of eigenvector that came out of the calculation. Just need to do 2 iterations. So we're going to take this one. We take 1 minus 1/4 and 1/4. 1 minus 1/4 and then 1/4. And then we multiply. So this by this is going to be minus 1/3. And this by this is going to be, it's just right here. So this by this is going to be minus 1/3. This by that is going to be minus 1/12. This by this is going to be 1/3. So this cancel out, giving us minus 1/12. Okay, that's what we have. So we continue, we do the next one. This by this is going to be 5 out of 6. This by that, it's going to be 1/12. This by this is going to be minus 5 out of 24. Right. Okay. So that's what we have. 24. So you divide this one by 6, you get a 4. You multiply, you get a 20. 2. Which is 22 minus 7. Minus 5. 17. So need to make sure we're getting the correct answers here. Right. So okay. And then the most bottom one, you multiply this by this, you get minus 1/3. And then this one is going to be minus 1/12 plus 1/12, leaving us with only minus 1/3. Okay, I need to just be careful that we're getting the correct answers. Just a sec. Okay, so with this, you have 1, 1 out of 4, my goodness. Okay, and then we continue, and then we have 1/4. What's the answer? It's exactly that one there. Okay, good. So this is the correct vector on the right. Now with this, then we continue and we analyze the November 2023 paper, and we then say, which one is the biggest of all of them here? 6, because this one is 0.3. This one is bigger. Okay, if we divide 17 by I'm just checking here, 17 divided by 24. Right, is a 0. This. 0.3. So this is the dominant one. So you're going to pull this out. And if you pull out 17 out of 24, you have a 1. So if you pull out 17 out of 24 out of this, and pull out 17 out of 24 out of these. Okay. Right, okay, let's first pull out 24 out of this. So now, okay, let's just work out the algebra a little bit to make sure we do the factoring correctly. So in other words, if you are to multiply these by 17 out of 24, you have minus 1/12. What would you need? You would need 24 out of 17, so that when you multiply these by this, it becomes exactly that. So factoring out 17 out of 24 is going to introduce the inverse, the multiplicative inverse. And then that would mean this 12 divides, and then you have minus 2 out of 17. Okay. So okay, you pull out 17 out of 24 out of this. But we wish that, okay, when we multiply this minus 1/3 by 17 out of 24, then you have 24 out of 17. Right, so if you pull out the 17 out of 24, then you're going to have this minus 8 out of 17. Like this. Right, so that when you take this thing here, you multiply it by 17 out of 24, it becomes exactly minus 1/3. So you have that. Okay. Just some algebra. Now, with this said, with this mentioned, what is the conclusion? Okay, obviously, because it was an exam question, so the iterations are not too many. Like, use the power method to estimate the eigenvalue of least magnitude and the corresponding eigenvector. Start with this one and do 2 iterations. I'm going to do just 2 of the iterations. So we have exactly that. So after 2 iterations, right, after 2 iterations, we make an observation. After these 2 iterations, we estimate the dominant eigenvalue of A inverse as okay, so the dominant one becomes this. S 17 out of 24, which can be estimated 17 divided by 24, 0.70. 8. 3 recurring. And the corresponding eigenvector. And the corresponding eigenvector is x equals, what is the eigenvector? It is exactly this. So you can write it as minus 2 over 17 minus 2 over 17, 1 minus 8 over 17. Like this. Okay, and obviously you can look at this and find this in the memo. And in the memo, it's going to be estimated like 2 out of 17 is minus 0.1176. 1, 8 out of 17. 0.4706. Okay. Then this is what we have. Like so. Now with this, we have solved this question in detail. Just 2 iterations, we found after 2 iterations, we estimated the dominant eigenvalue of the inverse and the corresponding eigenvector. But now we're not done solving this question because we need the eigenvalue of least magnitude. Thus, the eigenvalue of least magnitude, which is what they want, of A is therefore lambda equals 1 over this one, over the 17 out of 24, which is the dominant eigenvalue of the inverse of A. And therefore, this is this. Twenty-four out of 17 is what? Approximately 1.4 11 76. Okay. And the corresponding eigenvector the corresponding eigenvector is the same one. Minus 2 over 17. 1 minus 8 out of 17. Okay. All right, so we do another question now. The next question, it's a question that came also in November 2023 on numerical methods. And it is the most popular Pade approximation. This appeared as part of question 4 of the November 2023 exam. Find the Pade approximation with numerator of degree 2 and denominator of degree 1. Of degree 1 to the function f of x equals x squared plus x cubed. Look at the solution to this. Yes, Rutila? Yeah, okay, I'm in class now when I'm done. All right, thanks. All right, so now we continue with this Pade approximation, and also we look at how this problem can be done. Obviously, this one is not a very difficult question, but it's also not very, very lengthy. It's quite short. Let us look at this and see how well we can do this particular question in a way that will allow us to find the Pade approximation of this one. Find the Pade approximation, numerator degree 2 and denominator degree 1 of that particular function. Very straightforward. Let's just have a discussion about the method here. Solution. The couple of things obviously we need to consider as we consider the Pade approximation of these is to say the Pade approximation is the R of x, which equals a0 plus a1x plus a2x squared. Divided by 1 plus b1x. Okay, obviously it is consistent with the fact that now the Pade approximation is that one because the R3 of x with numerator of degree 2. So we can see the numerators of degree 2, it is a quadratic, degree 2 there. And the denominator of degree 1 is linear, but we always make this one a 1 to avoid the denominator being 0. We stated that last time. To the function these, okay, so we have that. Now let's continue with this. What does this give? So this yields R3 minus f of x. We subtract them. And by subtracting them in this manner, because we want to find the approximation to f of the R3, so but R3 is exactly this, which is a0 plus a1x plus a2x squared divided by this one minus the f of x, which is given in the question as x squared plus x cubed, like so, which simplifies to right. So now we can actually therefore simplify this. A0, a1x, a2x squared, 1 minus b1x, x squared plus x cubed, divided by this is a plus, divided by 1 plus B1x. And then let us see what this gives us. It's A naught plus A1x plus A2x squared. If you distribute here, it is minus x squared minus x cubed minus B1x cubed minus B1x to the fourth power divided by this. We continue. Okay, so let's take this one now and continue to solve this particular question. But to solve it in detail, right. We have still R3 of x minus f of x. And then that is going to become something similar to this. It's just going to become this. Okay, there's only one constant term, A naught. A naught. And then how many linear terms in x are there? There's only this one. So it is plus A1x. And then quadratics. X squared terms is going to be this quadratic and that quadratic. So it's going to be A2 minus 1. So x cubed is going to be this one and this one. So you pull out. So it's going to be minus into 1 plus b1 into x cubed. Into 1 plus b1 into x cubed. Okay. Like so. Fourth degree is 1. It's minus b1 x to the fourth power. Which is exactly the same as 1 plus b1x. Like this. To find the 4 unknown values, we write the following comment so that this can be remembered and one can know exactly what's happening here. So in the Pade approximation, we proceed to find the 4 unknown values. A0, A1, A3, B1, we must set the coefficients. The coefficients of x naught, x1, x2, x3,
in the numerator, to 0. This gives us the equation. Gives us the equation. Right, in particular, it gives us the equations, which are many. So to find the 4 unknown values here, we can see there's A0, there's A1, there is, for instance, A2, okay, yeah, A2 here. Right, and B1, A0, A1, A2, and B1. We must set the coefficients of x to the naught, 1, 2, 3. X to the 4th power in the numerator equal to 0. This gives us the equations. What are the equations? So, for example, we can see that if you set this to be equal to 0, because we want these to be equal to this. So if these are equal, then the difference between the two functions is 0. So it's the 0 polynomial. Wanted this to be equal, so it means A0 is 0. Okay, if A0 is 0, then means also A1 is 0. But it also means that A2 minus 1 is 0. And then that means 1 plus B1 is 0. Let's see what else. It means also that B1 is 0. It means B1 is 0. The conclusion and the observation, therefore, is that A0 is 0, A1 is 0. A2 is 1, B1 is minus 1. Okay, very strange things here. Hence, the Pade approximation is R3 of x, which we saw is A0 A1x plus A2x squared, 1 plus B1x. A0, A1 about 0. A0 is 0, A1 is 0x. But you can see that A2 is 1. X squared divided by 1. What is B1? Right,
taking -1 implies that R3 of x is exactly x squared out of 1 minus x. So this gives us the Pade approximation. Okay, I'm looking at this very keenly, the sort of contradictory statement here about this b being -1, 0. It's a very interesting observation. It's a very interesting observation. Okay, but it's contradictory anyhow. And so it's very important that you take this with much caution. Provided I'm just looking very carefully to avoid this. Okay, so we can stop it because of this. I'm going to give a comment here. Because this one is of degree 3, highest degree 3. Necessary give this comment. We must, okay, find the Pade approximation R3 with the numerator of degree 2 and the denominator of degree 1 to the function this. And this function has highest degree 3. Okay, because there's highest degree 3, yeah, you can take up to, you can remove this one. You can wish, therefore, that the top is sort of third degree. So that we disregard this part. And therefore, we're going to rely on this. This is the highest. And therefore, the B1 is going to be -1 denominator, and we have these. Right, and that's by and large what we wanted to sort of discuss here. But today, looking at the time, I think we discussed these couple of things we discussed. So, but I'll continue tomorrow to have a discussion about more things. There are still things that are remaining. But by and large, the finite difference method has been discussed and better simplified, and to some extent, it's becoming much clearer now, I believe, and a bit more familiar. The finite difference method and other associated methods like your Pade approximation, they are much clearer now. And the power method as well that we discussed today. The shooting method is something I'm still planning to come back with more problems, but we were able to discuss the power method today. Yeah, I mean the shooting method, we drew some distinctions, the advantages and disadvantages of the shooting method against the finite difference method. So it's a developing thing, the shooting method. I want us to spend a bit more time on it with the interpolation formula and just to have a sense of what it means to discuss these methods here. Okay, and otherwise then I must thank you for joining us today, and then we shall meet again tomorrow. I'm planning 4 p.m. So let's just keep it at 4 p.m. It's a little bit, it's better. It's not too late. It's a bit late, but it's not too late, but it's good enough. 4 p.m. Okay, I must thank you for joining us and see you tomorrow at 4 p.m. Thank you and goodbye.